This video we will look into an example of mass conservation. So here we have a container. This is scenario number A and this is scenario number B. So for A, you will have some flow rate coming, and this is 2 kilograms per second. And B also have the same flow rate coming. However, for A, we will have no mass flow rate leaving, but B will have mass flow rate coming out. It's 1 kilogram per second. So we needed to find how much water is stored after 5 minutes. For A and B. Then the second question we need to ask is how long if the tank is 12 meter cube. Okay, then how long would take to fill the tank? Well, so this is actually a mass conservation problem. Now let's take a look. How do we solve it? First of all, we need to go ahead and label this. This is mass flow rate coming, right? And this is our mass flow rate coming out. And they have the unit of kilogram per second, mass per time, that's mass flow rate. So from the previous video, mass conservation concept, we know the change of the mass inside the system over time is going to be equal to the mass flow rate coming minus mass flow rate coming out. That's our mass conservation equation. Then for scenario number for A, what is our mass flow rate coming? 2 kilograms per second. And what would be the mass flow rate out for A? There's 0, there's no leak, right? So in that situation, then we can quickly plug into this conservation equation. Then delta M over delta T is going to be 2 minus 0. That's equal to 2 kilograms per second. Then the question is, what's going to be how much is stored after 5 minutes? Initially, there's no water at all, right? So now it's going to be increasing because there's more coming than leaving out. There's actually nothing leaking out. So every second of time, there are 2 kilograms of water increase in this container. And after 5 minutes, so we want to solve this delta M. How much increase? How much water is stored? So delta M, that's going to be equal to this 2 kilograms per second times our delta T. And our delta T is how much duration? It's 5 minutes, right? 5 minutes. And each minute give us 60 seconds. So knowing that, we can calculate the entire time. For 5 minutes of time, how many kilograms? So 2 times 5 times 60, that's going to be 600. 600 kilograms of increase of the mass. That's how much mass was stored after 5 minutes, right? Okay, so that's help us figure out the first problem for A. Now we're going to figure out for B. That would be the same logic. For B, mass flow rate is also 2 kilogram per second. However, mass flow rate coming out is 1 kilogram per second. So knowing that, bring up to our mass conservation equation, the mass change means how much has stored up, right? Because initial is 0. Over delta t, this 5 minutes of time, that will be mass flow rate coming in minus mass flow rate coming out. That will be 1 kilogram per second. That means every second you will see 1 kilogram of mass increase. And you want to see how much exactly this mass increase during 5 minutes of time. So if you're solving this, would that be delta t times this 1 kilogram per second, right? This delta t is also 5 minutes, and that will give us 300 seconds. Then times 1 kilogram per second. That gave us the answer of 300 kilogram. So during 5 minutes, you will see 300 kilogram of mass or water stored up in the container. All right, so sometimes you might say, oh, this is really redundant. I can work out those numbers in my head. You know, I got the same answer. I agree with you. But I want you to thinking about problem number 2, because for this, it sometimes might not be that intuitive. And however, using this mass conservation will help us to get overcome that barrier. Now let's see what I mean. So the question number 2 is like, if this tank is 12 meter cube, then how long will it take it to completely fill the tank, right? Again, this is the conservation equation, conservation mass. So delta m over delta t is equal to mass flow rate coming minus mass flow rate out. And how much will it take to fill the tank? Actually, I'm going to add it for A and B because they're going to have a different time, right? Okay. So now let's start with for A. For A, delta M over delta T, that's going to be mass flow rate is 2, mass leaving is 0. And what's going if to complete fill the tank? So initially, M initial is 0. There's nothing in the tank. And then final mass is completed full. Completed full, we know the volume, but we need to know the mass. So mass, we know it's volume times density, right? Because we know density is mass over volume, so mass is going to be equal to density times volume. So knowing that your volume here is 12 meter cube, and the density of the water is 1,000 kilogram per meter cube, then you get 12,000 kilogram. So that means to complete fill the tank, there are 12,000 kilogram of water. Initially, there's empty, nothing. So what's going to be this delta M? From nothing at all to complete fill to the brink. That will be 12,000 kilogram. So knowing that, we can go back to this mass conservation equation. You have 12,000. And how long is this process? That's what we are solving. And with this condition of mass flow rate coming in and mass flow rate coming out, then we can go ahead and solve our delta T. That will give us 6,000. 6,000 of what would be second? Because this is 2 kilogram per second. This is kilogram. So delta T will be second. And 100. So that means it's exactly 100 minutes, right? Okay. So that's for scenario number A. And now I want you to thinking about how to solve for B. For B, intuitively, you know it's going to take longer because there's some leak during the process, right? But however, we're using the same logic, and I encourage you to go ahead and do this by yourself and then come back to check, see if it's the same answer. So delta M over delta T is going to be mass flow rate coming, which is 2, and however, mass flow rate out is 1. And we here has the same. From empty to completed full, the delta M is 12,000 kilogram. Then plug it in. And how long will this process take? Delta T is what you are solving, equal to 1 kilogram per second. Then we can find our delta T is 12,000 seconds. 12,000 seconds divided by 60, that will be 200 minutes, right? Okay, so that's concludes the example on this mass conservation problem. All right, okay, I'll see you at the next one. Bye.